Welcome to the exercises for Chapter 9, focused on applications of differential calculus. Let's begin with exercise 1, which focuses on linear approximations. This was the first application, the first topic that I introduced in the beginning of this chapter. Okay, so what you want to do in this exercise is fairly straightforward. Basically, you just need to translate the math formula that I showed in the text into Python code, in particular using SymPy and symbolic expressions. So write a Python function that takes four inputs: a function, its derivative, the desired point. This is the point that we want to approximate, and the starting position, which I call here x sub s. Okay, I will scroll up in a moment and show you that equation as a reminder. And then you can test your code by running through the first example problem that I showed in the book. And your linear approximation should be 10.8325, and then lots of zeros after that. And then the SymPy calculation of the exact result, or at least, something that is very close approximation to an exact result, should be this crazy number here. Okay, so if you can get this output using the the example problem that we worked through in the beginning of this chapter, then you can be comfortable that your linear approximation code is correct, and then we can continue exploring it in the next exercises. Here is the formula for the linear approximation that I just mentioned. So f of the value that we want to approximate the function at, so x of sub a, is approximately equal to the derivative of the function times the evaluated at the starting point times the delta x, basically the difference between the approximation value and the starting value, plus the value of the function at the starting value. Now, in this part of the chapter, in this section, I discussed how to think about this function, and basically it's just a formula for a line. So we have y equals mx plus b. So it's literally just the formula, the equation for a line, with slightly different variable names to get this linear approximation to work. Okay, and then we use this formula to test our Python code. So the function is the square root of x plus 2x, and we want to evaluate the function or approximate the function at 4.37 using a starting value of 4. Okay, so if you implement all of that, you should be able to reproduce the results that I showed a moment ago in the exercise text, which you also see here in the main text. This exercise was, I hope, not too difficult for you to solve in Python, but a great opportunity to explore using code or translating math formulas into code. Okay, so here I call the function linear approximation. It takes as inputs a symbolic variable expression f, the derivative, the approximating point, and the starting point. And then here, this is just the translation of that approximation formula into SymPy code. Okay, so we have the output. This is y equals the value of the derivative at the starting point times delta x plus the value of the function at the starting point. All right, so run that piece of code there. Of course, it doesn't produce any outputs. I'm just defining the function in this code cell. And here I am actually implementing the evaluation. So create a symbolic variable x. I define it to be the function square root of x plus 2x, compute its derivative, and then here I'm defining these two values, running the function, and printing out the results. Very nice. Okay. Welcome to exercise 2 of chapter 9. Here we will continue working with the linear approximation function that you created in the previous exercise. And now what we are going to do here in this exercise is explore how the approximation error varies depending on the starting value. Okay, so what you want to do here is take the linear approximation function from the previous exercise, put it inside a for loop, where you're looping over a range of starting values. Okay, so the initial guesses, this is x sub s, and in a for loop, you range over 5 to 14. And now the approximating value is going to be 10. Okay, so the values that we're using are a little bit different from those in the previous exercise. Remember, in the previous exercise, we evaluated the function using a value of 4. So now you want to approximate the value of 10, same function as in the previous exercise, starting from various numbers from 5 up to 14, and then collect those errors inside the for loop and then make a plot of what those errors look like. I will have a couple of things to say about interpreting this graph when we switch to Python. So here I define the starting values. I'm using 30 numbers between 5 and 14. So this is the list of x sub s, right? The starting values. And here's x sub a. This is the value that we want to approximate using the function. Okay, and then here is the true value of a, and that I'm getting simply by substituting in for the function. Wherever we see x, then we substitute in for 10. So this is going to be our ground truth that we will use to evaluate the accuracy of the linear approximation. Okay, so here I am just initializing some variables so I can collect the results. Okay, and here's the for loop that runs the approximations. Not so difficult. Basically, all I do is have a for loop over these starting values. I call the linear approximation function. This is the function that we wrote in the previous exercise. And then here I'm just subtracting the true value minus the approximated value. And then I'm making a plot of those approximation values. Okay, now I want to actually go back and have a little discussion about the function I wrote in the previous exercise. You might have been wondering why I have this input be the derivative. Why not say, just have 3 inputs, and then inside this function, say df equals sim.difff. Now, this would be perfectly acceptable. It's completely fine. This is, in fact, the same thing that I'm doing here. Just here I'm implementing the different derivative calculation outside the function, and here it's inside of this Python function. But there is a reason why I decided not to differentiate inside this function, and instead to differentiate outside the function and then take the derivative as a separate object like this. And here's the reason. The reason is so that we can save computation time in a for loop like this. So imagine that this function needed to recalculate the derivative of the same function 30 times, which is not even that many. That's going to increase the computational cost of running through that function. And it's completely redundant because we'd be recalculating the exact same derivative over and over and over again 30 times. And maybe if we wanted higher resolution, we'd be calculating the derivative 300 times, and 299 of those times would be completely redundant. So that is the reason why I chose to set up the function the way I did. Okay, all that said, now we can look at this graph. So what do we see here? We see that the errors are getting larger as we move further away from the approximating value. That makes sense. We want to know the value of the function at x equals 10. And when we use an approximating value, a starting value of 5, that's far away from 10. So, it's no surprise that the error is going to be larger. You can also see that the errors in this case are always negative. Now, that is not a trivial result of linear approximations. They're not always going to underestimate. That just happens to be the case for this particular function, and that's because because the nature of the derivative and the function is bending upwards. It's concave. I have a more discussion about this in the chapter in section 9.1 when I introduce this method. And yeah, I guess it's also interesting to see that it's really, really accurate when we are very close to the target value that we are trying to approximate. Now, on the one hand, the shape of this function, that the errors get larger as we get farther away from the approximating value, the target value, it's not very surprising but it will be pretty interesting to compare what this plot of the errors looks like with a similar plot in the next exercise. Here we are with exercise 3. This is a follow-up to the previous 2 exercises on linear approximations. In fact, what you want to do in this exercise is essentially reproduce the previous exercise or rerun the previous exercise, but using a different function and, of course, different starting and approximation values. Okay, so use the function f of zeta. It's a beautiful, elegant looking Greek letter zeta equals the absolute value of the sine of zeta. That is the function. And then you want to use, try the approximation function just once. We don't have to worry about a for loop just yet. So try to use this function to approximate the value of f of 5 pi over 8 using a starting value of pi over 2. And then you're going to get some crazy looking result that looks like this. You're going to have to figure out whether this is bad, how to interpret this, why this might be a problem, and ultimately how to resolve this issue. So that is part 1 of this exercise. Once you have figured this out and come up with a solution, then run a systematic relationship between, or explore the relationship between starting values and errors systematically using starting values in the interval between minus pi and 2 pi. And then, so these are the starting values, and then the approximation value is the average of all of those starting values. Okay, so define some linearly spaced vector between minus pi and 2 pi, and whatever is the average of all of those starting values, that is what you use as your zeta A, your approximating value. And then you make a similar plot visualization as in the previous exercise, and it's going to look something like this. It looks qualitatively quite different from this error plot that we saw in the previous exercise. So I'm going to have a couple of comments about this when I get to that point in Python code. So far, a lot of this code is really just copy pasted from the previous exercise. I redefine a symbolic variable x. Here is the function in SymPy, the absolute value of the sine of x. I guess I could have used zeta here instead of x. But anyway, and here I calculate the derivative. Okay, so far, everything is good. We don't have any warning messages or error messages. Everything seems fine. Here is the approximating value and the starting value. And here I just call the function. Again, nothing weird going on here. Okay. And now we get this funny looking result. Now, maybe you think this isn't a problem. We should just ignore it. Because again, there's no error messages or warning messages. It's just that the output is not in the form that we might expect for the output of this function. Okay, but we are going to start running into problems when we try to continue using this code. And scrolling down, we see we get this type error cannot convert expression to float. This is a similar issue to what we encountered in the previous chapter, in the exercises of chapter 8. We also discussed these kinds of error messages. Now, when you look at this, one hint that SymPy actually is still doing the right thing, is still calculating the right answer, is that, you see this number here, this is 2.4 something times 10 to the minus 17. So this is essentially 0. And here, this is something to do with the derivative being evaluated at a real number of, pi over 2. But don't worry about this. You can see that whatever all of this stuff is, it's the product of something that looks weird with 0. So immediately that should be ringing alarm bells that you're just multiplying stuff by 0. So it doesn't really matter what's going on here. Okay, so we have 0 times something plus 1. And this is the key insight, right? So this is actually the correct result because we're essentially saying 0 plus 1. And we know we calculated analytically in the book text that the answer to this problem should be exactly 1. Okay, and yeah, here's my hint. What field is x in? This obviously is, doing something with real valued or real parts of the number, so we can guess that there is some complex numbers going on here. So what we can do is just constrain this symbolic variable so that it can only take on real valued values. It cannot be complex valued. Okay, so I add that constraint to sim.symbols, and then I run this again, and now we get a value of 1, as we expect for real valued mathematics. And this is also consistent with what we saw in the book text. Okay, and then I can rerun this code. Now, I'm not going to walk you through all of this code. It's literally copy pasted from a couple the previous exercise. The only thing I really changed is this. So now I'm going, from minus pi to 2 pi in 99 steps, which, before it was 30 steps. Otherwise, it's all the same code. Okay, so now we get this interesting looking graph, which kind of looks like Dali's mustache. I think right here would be his nose, and here's the his crazy mustache. Now, what do we see here? This looks qualitatively different from the error graph that we got in the previous exercise. And the key difference here is that in this exercise, we're using the sine function, which is cyclic. So it keeps wrapping around over and over again. So as we are cycling through the sine function, the errors, the approximation errors, are going to flip in sign, and they're also going to get closer and further away and closer and further away. And so to demonstrate this even more, it's interesting to plot out in a larger range. So 2 pi minus 2 pi to 4 pi, for example. And now we see the same pattern. We still get all of these errors, and we still see this cyclic pattern of approximation errors. Of course, close to the approximating value, we do get a pretty good result. And that is generally always going to be the case. The closer the starting value is to the approximating value, the more accurate the approximation is going to be. I discussed this in the chapter, some reasons why this is sensible, especially for nonlinear functions like the sine function. But this also does have practical applications and implications, namely that anytime you are doing linear approximations of nonlinear systems, you can more or less trust that the approximations will be quite accurate as long as you are using linear functions that are close in numerical values to the nonlinear functions. Now that we've done several exercises on linear approximations, let's switch to Newton's method for finding roots. So this exercise and the next 3 or 4 exercises are all related to the same concept, which is using differentiation to estimate roots of equations using Newton's method, which I described in I think it was section 2 in this chapter. So to start with, in exercise 4, here you want to write a Python function that implements the Newton's method. And actually, all of Newton's method is iterative. So what I want you to do is write a Python function only to implement equation 923. I will scroll up to that equation in a moment. And then basically all the iterations that are calling equation 923 are going to be done outside of that Python function, for example, in a for loop. Okay, so write a Python function that takes 3 inputs, a SymPy function, a SymPy derivative, so symbolic variables for the function, the derivative, and the current estimate of x sub n. Okay, so those are the 3 inputs to your Python function, and what your function will output is the updated estimate, x sub n plus 1, based on Newton's method. Here is the equation that you will implement in the Python function. It's very straightforward. All you do is take the current estimate of the root of the equation and subtract the ratio of the function to the derivative at that same point. Okay, so we have our estimate of the root, and then basically we change that root, we update that estimate according to this ratio. So your Python function will implement this right-hand side of the equation and output this updated estimate of the root on the left-hand side of the equation. Once you have written that Python function, test it on this equation. 2 times x cubed equals 3. Now, we already know a couple of things about the roots of this equation. First of all, there are going to be 3 roots to this equation. However, 2 of those roots are going to be complex valued, and 1 of those roots is going to be real valued. And we know that only 1 root is real valued because you can solve this, well, just because you see it's just a polynomial. It's a third order polynomial with no other x terms. So it will cross the y equals 0 axis exactly once. So we want to use SymPy to find the real valued solution to this equation. So we want the exact solution, and then you want to use Newton's method to estimate that solution, to approximate the real valued root. So run just 2 iterations by calling the function twice. You don't have to worry about setting up a for loop here. You can just run the function twice. And then print out your results like this. The results here are spread across 2 pages, but basically we start with the initial guess of 0.8, and then the first iteration, the second iteration gets us to 1.166, and then the analytic root, the exact root that we solved for using SymPy, is 1.145. Because we can already anticipate that we are going to get some complex valued numbers floating around in here, I'm going to preemptively restrict the field to be real valued. Okay, so I'm including this code real equals true when I create this symbolic variable x. All right, here is the function, and here is the derivative of that function. Now remember, I've said this many times. This is what we are trying to solve. Implicitly, what we do is set up this equation here. Okay, so we subtract the right-hand side from both sides of the equation, and we have a function that is implicitly set to 0, which is how I use sim.solve. Okay, and then we find that the real root is 2 to the power of blah, blah, blah. Let's see, I can eval f. Okay, so the real root is 1.14 and so on. Okay, so now here is the Python function to implement 1 iteration of Newton's method. It's very simple, as I showed in the equation in the book. So we just take the current estimate, and then we subtract off the function value at that current estimate divided by the derivative at that current estimate. And that is 1 iteration of that algorithm. Okay, and then here I start with our initial guess of 0.8, and then I run through the function once, and then I run through it again. And notice that the input to this second update is the output of the first update. Okay, again, in this particular example, I'm only running it twice. We don't need to use a for loop here. Okay, so this is the output. Now it's interesting to compare. You can see the root was initially too small, right? This is the target number that we're looking for. So we started off being too small, and then we actually overshot, right? So the first update from Newton's method went too far over the actual root. But then the second update was much closer. And you can run it for a third and fourth update, and you will find it's going to keep getting closer and closer. That's actually what we are going to explore in not the next exercise, but the one after that. Okay, so before moving on to the next exercise, I encourage you to spend a few moments and just play around with this x naught value. So try different values of a first guess, but do not try 0. So don't do this, because that is the starting point for the next exercise. Exercise 5 is a direct follow-up to exercise 4. What you want to do in exercise 5 is start by running through Newton's method again with the same equation as in the previous exercise, but this time set the initial guess to be 0. That is the value I told you not to try in the previous exercise. So start with an initial guess of 0, and something bad is going to happen. And then the issue is, well, what is the issue? Why did something bad happen? Yeah, what's the problem and why did it happen? And then you can think of a couple of ways to try to resolve this issue that we have discovered. All right, I call this here Newton's failure. Let's see. So here I'm running exactly the same code as I did for the previous exercise. Same symbolic function, same symbolic derivative. The only difference is in the previous exercise, we started off with an estimate of zero point 0.8, and now we are starting off with 0. And we get some funny looking, approximately infinity sign. So this is something is going wrong here. This is definitely not a valid root of the equation. So what's the problem here? Well, let's look back at the algorithm that we are implementing or the equation that we're running. So we have the current estimate, no problem, that's 0, it's fine, and then we are subtracting off a ratio. Now, when the function has x equals 0, that's no problem. Here's the function. It ends up being 0 minus 3. So that's we get answer of minus 3 when x equals 0. Totally normal numerator. But check out what happens to the denominator. So the derivative of this expression is, let's see, so we have 2 times x cubed. So that term gives us 6x squared. And this is a constant. So the derivative here is 0. So basically we have 6x squared. And when we substitute in for 0, we get 0. So that means we are dividing by 0. So that is a failure scenario of Newton's method. It can happen that if the derivative is exactly 0, where you get an estimate, then you're going to you're going to end up with something divided by 0. And that's the issue. So here's just a little cute analogy. A marble cannot roll downhill on a perfectly flat plane. So that's kind of what we're doing here, where Newton's method is bouncing around, getting us closer and closer to the root. But the direction and the magnitude of those bounces depends on the derivative. Okay, there's a couple of ways you can fix the problem. You could try adding a tiny offset. So for example, we can try this. So instead of starting at 0, we're going to start at some small number like this. Now, on the one hand, this is okay in the sense that we get a finite number instead of infinity. So that's better, but also this is hardly close to the root of the equation, which is essentially just x cubed. You could just keep running this over and over again. Let's start here. So let's say 0.0001. Let's do this. So you can see we started off super far, but already we're getting a little bit closer, right? Now, maybe, slightly less extreme. Just so you can see with more iterations, we're going to get eventually closer. Maybe, I don't know, you could try this yourself. Maybe it takes 10 iterations or something, but eventually it will creep back down to a good approximation to the actual root. So that's one thing you can do. You can also start by picking a random number. There are numerical methods that will allow you to start with a decent approximation of a root, so you can avoid issues like this. But mostly, I wanted to have this exercise so you can see for yourself one of the failure scenarios of Newton's method, and just in general, these kinds of methods for approximating solutions to equations. Now, in a situation like this with, a single variable equation, or maybe even a two variable equation, these are not such serious concerns. But consider that people also try to apply these kinds of methods to find roots of like 20 variable functions or 100 variable functions. So in these cases, the complexity of the problem is really, really high. And it's literally impossible to visualize a 20 variable function. And so these may seem like toy concerns in this very simple case, but these do become very serious issues in applied mathematics. Here in exercise 6, we will continue to explore using Newton's method to approximate roots of equations. Okay, so the goal of this exercise is to write code using a lot of Matplotlib and NumPy that produces figure 9.4. I will scroll up to that figure in a moment. And basically, it's just visualizing Newton's method iteratively on this equation here. So 3x cubed plus 2x equals 7 pi. Now, we are only interested in the real valued root of this equation. So where this equation crosses the y equals 0 line. Now, there's going to be three solutions in total, two of which are complex valued and one of which is real valued. So you have to figure out how to get SymPy to return only the real valued root. It's a little bit tricky. It might take some trial and error. Maybe if you don't look at my solution, maybe you want to just look around the internet a little bit for some help or ask ChatGPT to give you some pointers. But I think this is a great opportunity for you to become more familiar with the inner workings of SymPy and just using SymPy in general. Okay, here is the figure that you want to write code to reproduce. So we have x and y is the function values. This is the description, the definition of the function. Here you see the function, and it's pretty obvious here from looking at this black line that the function will have one real valued root, right? It's going to keep going up to plus infinity this direction and down to minus infinity in the negative direction, and so it crosses the y equals 0 line exactly once, which is right here. Here I have calculated the exact root using SymPy, and that is 1.83 approximately. And so here's the first iteration. We started off with an approximation, an estimated root of 1. And then, we got this estimate over here from Newton's method. Notice that, this overshot, right? This was too large. And then the next estimate was closer. And then the third estimate already was really close, and you can run a couple of more iterations and it will get even closer. But this is quite good, I think. Okay, so this is the figure that you want to write code to reproduce. So here is the definition of the function, again, implicitly set to 0. And here is its derivative. And here I'm trying to use sim.solve to solve for this expression. Now, the variable x here, I defined this a few videos ago, or a few exercises ago, up here, and I specifically said that x is only for real valued solutions. In fact, I'm even going to rerun this again to convince you that I'm running this line of code, defining x to be with this constraint that it should only incorporate real valued values of x. Nonetheless, when we write sim.solve, we get lots of text here, but what I want you to see is that this includes the letter I, the capital letter I, which is the SymPy's symbol for the imaginary operator or the square root of -1. So that means that that SymPy is still returning complex valued solutions to this equation. Okay, now one thing you can do is just look at these individually. You can see this solution is a complex number. The second solution is also complex valued. Here, for example, is a I here. But the third solution is a real valued number. So there's no i's, and here there's no square roots of -1. This is a real valued solution. It is absolutely mind-bendingly crazy, to have this cube root, the square root inside a cube root, and so on, but that is what the solution looks like. Okay, and if you want a number, you can write .evalf, and this is the numeric approximation of this number. Okay, so this is one way. You can just take the look through the set and pick out the one that has a real valued solution. Now, you can also try running this, real roots. This is a SymPy function that will identify the real valued roots of a problem or an equation. And unfortunately, it's just not really doing very well here. This is a case where there is a real solution, but this particular function is just not really able to find it. Okay, another method you can use or function in SymPy you can use is called solve set. This is related to solve. There are some differences between the function solve and the function solve set. basically solve set is more advanced. It has more algorithms built in. It can handle different types of equations, but the output can be a little bit more complicated to work with. Okay, so here we see the three solutions in this set, right? We have this curly bracket here. So this is a set that simpy.solveset is returning. You can see we still have complex valued solutions in here. Okay, so one thing we can do is restrict the domain to the reals. Okay, so now we are saying solve this equation for this variable, but only in the domain of the reals. Okay, and then that gives us one solution, and that looks the same as what we got from the third solution from sim.solve. Okay, and now this is a simpy set, which is its own type of object. We can see here, type. So this is called a set, and in particular, a finite set. So if you want to extract the actual data from this set, you can use .args. So args for arguments, those are the elements in a simpy set. And there's just one element, so we only want to extract that first element. Oof, and there we go. So I hope you feel like you learned something about working with simpy from this exercise. It's simpy is powerful, but it can be weird and tricky and sometimes not very intuitive. Anyway, now we have the real root. Now the next goal of this exercise was to generate that figure. Okay, so here I lambdify the function so that I can call it in plotting and evaluate it for particular numerical values for estimates of the root. And here are the values I'm going to use for the grid, so -1 to +3. Here I'm just generating a plot of the function here, and here I'm plotting the real root with those dashed lines that I showed in the figure in the book. Okay, and then what I'm doing here is specifying the number of iterations and the starting value to loop through Newton's method for approximating the root, now that we have the exact root. Yeah, so basically I'm just plotting the value of our estimate of the root and the function value at that x-axis estimate, and then I'm updating x naught. Okay, and the rest of it is just, some things about setting the color and so on. Here's the legend and so on. Okay, so this reproduces the figure in the book. Now, I initially wrote code to also show the tangent lines at each estimate. And I thought this would be nice because it kind of shows the mechanism of the update. But in the end, I kind of decided that it was just making the plot look a little bit too busy, a little too much stuff going on. But I decided to leave this code in here in case you find it helpful. Maybe you want to update this, change the colors instead of grayscale, making these updates be different colors. Yeah, I will leave that up to you as an optional exploration. Anyway, the last thing I want to mention about this code and this exercise is now that you have this code, I encourage you to explore how it works for different starting values. So try a starting value of, I don't know, maybe -1, try a starting value of 0 or 10, and maybe you will need to change the number of iterations. That's up to you, but I definitely encourage you to take some time and explore Newton's method using this code. Exercise 7 of Chapter 9 is one more exercise on Newton's method for estimating roots. This is basically following up from the previous exercise where we saw this plot of how the estimation, the approximation of the root of the equation got closer and closer with each iteration. So basically, the idea here is to continue exploring this convergence of Newton's method qualitatively in this demonstrative example by running through a for loop again and running through Newton's method for a couple of iterations and then making a plot that looks something like this. So here we see the iteration number. Iteration 0 is the starting estimate. This is the approximation, so the numerical value of the approximated root on the y-axis. And here I have the true value of the root calculated from SymPy on the in the dashed line. And then here's the estimate. So you can see that the estimate gets closer and closer with each iteration, except the first time we overestimated. And then, yeah, the algorithm quickly converged. So here I'm running through 5 iterations. And here is basically Newton's method, right? So it's very simple. We just run through all of these iterations, and then we keep updating. So here I have this variable x guess. That's our approximated x value of the root. And you can see I'm just updating it from the previous version to generate the new version. And then I'm just making a plot. A lot of these variables were created in the previous exercise or exercises before that. Okay, so far, yeah, this is not super difficult, I think, really complicated code here. But I wanted you to have this code so you can continue exploring the convergence from different starting values and for different functions. Now, this convergence, in particular, this really fast convergence, is not guaranteed to happen. Newton's method is not even guaranteed to converge onto the real root. There are failure scenarios, there are functions that are sufficiently difficult, and hopefully, if you use Newton's method in practice, you will get nice convergence, but that's not guaranteed. Exercise 8, which is this exercise, and also the next 2 exercises, are focused on using derivatives to find exact solutions to optimization problems in the context of word problems. So they're all going to have some format like this, where I give you some paragraph to read. It's always some weird backstory. And your task is to figure out what is the objective function, what is the thing you need to optimize for, how you can describe that or build a function for that optimization objective, and then use derivatives to find the exact solution. Now, this approach of having simple optimization goals that can be translated into pure math formulas and then getting exact solutions with differentiation, that's really great to practice. It's good to think about that approach to optimization. But in real world applications, it's not so often possible to use this approach. And that's because in real world applications, the optimization functions might be high dimensional, so multivariable. The functions might be non-differentiable, or maybe they have some discontinuities or some like difficult parts to them where where the derivative is not defined. Or maybe the optimization function doesn't even come from a mathematical formula that you can analytically differentiate. And instead, it might come from measured data. So in many cases in the real world, you're going to use alternative numerical approximations to optimization instead of this kind of, one-shot exact solution approach. Anyway, let us begin. Here's the problem. Farmers Fred and Fran are neighbors, and Fred wants to build a fence in the shape of a rectangle that shares one side with Fran, and Fran agrees to pay half of the cost of that side. And your goal here is to find the lengths of the sides that minimize Fred's fencing cost. Okay, now there's 2 tricky parts to this exercise. One tricky part is what's always difficult about these kinds of word problems, which is figuring out how to translate this text and this problem into a mathematical formula. The second tricky part, or actually the tricky part before that, is figuring out what do we even want to solve for. So you might be tempted to try to solve for area to maximize the area, or maybe to maximize or minimize the perimeter of the rectangle. But in fact, which is, the total amount of fencing. But in fact, what we want to minimize here is the cost. And now this is not the total cost of the fencing. It's only Fred's part of the cost. And Fred is only paying not for the entire fencing, but 3 sides of the fencing plus half of whatever side shares the wall with Fran. Okay, so it's not necessarily trivially going to be the case that the whatever the dimensions of the of the fenced in area are going to minimize the cost because, in fact, Fred wants to maximize the area that Fran shares because she's paying half of that. Okay, and then, there's lots of completely useless information, like who cares about their names, who cares about where they are, and also the price per meter of the fence literally does not matter. That doesn't change the cost function in the sense that whatever the cost is, it's still going to be minimized by the same mathematical function. So here in the code, I wrote text prose to outline the solution here. And the main thing I want to point out here is that the area and the perimeter functions are not relevant. These are not what we directly want to compute. These are not the objective functions. All we care about is the cost function here, which is 2x plus y over 2. The 2x is for the length of two sides, and then we have the side that Fred pays for, and then the side that Fran is sharing half of. Okay, so this function c is really the only function that we care about. That's what we want to differentiate, set to 0, solve for x, and so on. But I wrote down the formula for area and the formula for perimeter because it helped me come up with function c. And that is just an important thing to keep in mind about solving these kinds of word problems. Just write down lots and lots of equations, write down formulas and numbers. Even if they're not relevant, they might help you figure out what is the real function that you need to optimize for. Okay, once you have defined this function, and then, we also, so we actually do need the area formula to give us a constraint to solve for y in terms of x. So that's as simple as setting y equals 400 divided by x. And that is what I describe here. Now, once you have that, the math, the calculus is pretty straightforward. You just have to differentiate c and then solve for x. Now, in this case, we get two solutions, minus 10 times the square root of 3 and plus the 10 times the square root of 3 for x. And obviously, this solution does not make sense in the real world, so we easily discard it. Okay, and then here is code to make a plot. So you can see I am plotting the function c and the function, the derivative of c. And this is just used to confirm our answers. So here you can also see that when x equals 0, that is a critical point because the derivative is plummeting down to 0. That's an important point for the function, but that is obviously not a relevant point here. So here is the cost function, and basically you see it has a minimum here, and that minimum certainly visually coincides with where the derivative crosses 0. So this is the solution to C. It's not the solution to the problem because the problem description was not about the cost. The problem description was the lengths of the sides, and so you just have to be mindful that you give the final answer in terms of the question. So in this particular case, the math worked out to be approximately 17 by 23 meters, and the side of the rectangle that is longer, that is what gets shared with Fran. Here in exercise 9, we have another word problem about differentiation-based optimization. The approach and the concept is very similar to the previous exercise in that you just have to read the paragraph, ignore all the useless, distracting information, like the fact that our protagonist is a curious space alien, and try to figure out what is the objective we need to focus on, and how do we create a function for that, a mathematical formula for that objective, and then what is the final question that we want to answer. Okay, so Qbert makes enclosed boxes of 200 cubic centimeters, and the top and the bottom are squares. So this information here is giving us some constraints to work with that will help us define the function. Okay, material is expensive, and Qbert is an honest, hardworking alien. So the question is, what size of the edges for the cube will minimize the material's costs. Okay, so there's some information that we have to infer from here. For example, what are the materials costs? Well, there's like electricity in the factory to run, that's a materials cost. But there's no information about that here. So we just have to answer the question with the as best we can with the information that we are provided. So we have to assume that the materials costs that are relevant that we can minimize are the physical size of the boxes. Okay. So here I describe again the solution to the problem just as in the previous exercise. So here I write out the formula for volume. So that's x times y, and it's x times x because we know that the top and the bottom are squares, which means that the two of the three sides of this box are equal. So that's how I get to x times y. Now, we don't know what y is. We have to figure that out, but we can solve for y in terms of x. So we can say y equals 200 divided by x squared. And that is going to help us arrive at our formula for the surface area of all of the 6 sides of this box. So 2 times x squared, and that comes from the fact that the top and the bottom are squares, so their surface area is x squared, and there are 2, right? So the top and the bottom, so that's 2x squared. And then we have the 4 sides around the box, and those sides, the surface area of each side, is x times y, and this is y defined in terms of x, and then 4 because there's 4 sides going around the box. So this is our formula for the surface area of the box. And then from here, we can differentiate this, set it equal to 0, and solve for x. Again, here we arrive at a couple of solutions, but we can just consider the solutions that make the most sense. Okay, and then it turns out that x is a little bit less than 6. And then when we solve for y, we also get that y is the same value as x. So in fact, the size of the box that minimizes surface area is a perfect cube. All the sides are the same. Just keep in mind that the problem didn't ask for the volume of the box. It didn't ask for the cost. It didn't ask for the surface area. It asked for the lengths of the edges. So the final answer is that the lengths of the edges are around 5.85 centimeters. Okay, and then, that's all the hard work. That's the intellectual stuff. The coding here is just, having fun with Python. So the only way you can really, get this wrong is if you accidentally make a typo here, like set this to be x cubed or something like that. Okay, so here we see the optimization function and its derivative, and of course it's minimized at somewhere around here. Exercise 10 is a direct follow-up to exercise 9. In fact, the problem is the same. Our main character, Cubert, the curious space alien, is also coming back for a reappearance here. And basically, this is just a small modification. So the idea now is that we are redefining the problem because Cubert realizes that his boxes don't need to be covered. So now instead of Cubert's boxes having 6 sides, they will only contain 5 sides, right? So the volume could be the same. We're not changing the volume. We're just cutting out one of the sides, which means we're reducing the total cost. So now it's an open box. The volume is the same. The bottom of the box is still a square, but now there's no top. Okay, and then the question is, does anything change in the optimization function? So the good news is that you've already done most of the work for this exercise after having completed the previous exercise. We just need to figure out how to change the optimization function for 5 sides instead of 6 sides. Okay, so here in the online code, I have my written description. These two functions are the same. S here is slightly different. So remember in the previous exercise, this was 2 times x squared because we had two square sides, so the bottom and the top of the box. Now we only have a bottom of the box, so this is just 1 x squared. This term is exactly the same. The procedure is exactly the same. We still differentiate, set it equal to 0, and so on. But we actually get a slightly different answer this time. In fact, this is no longer a cube. And now another difference from the previous exercise is that the previous exercise asked for the lengths of the sides of the cube, of the box. And now here we are asked about the size of the faces. So here we actually want the area of each face. So we find that the base of the box, the bottom of the box, is x squared. There's one of them, and that's around 54 square centimeters. And then each of the four sides is around 27 square centimeters. Okay, and then here, yeah, so here I'm using a SymPy to give me an exact solution. Remember, this is the solution to x to one side of the box. So you need to then plug x into these expressions to get x squared and also to get y. Okay, and then here I show the graphs, and again, yeah, this just visually confirms the answer that we obtain algebraically.